Welcome all in our today's webinar, the second one in our webinar series. I will also like to welcome all those who are attending in person from our booth at SEDEX 2023 conference in Seoul. Thank you so much for joining us today. Please ensure that your microphones are muted and your video is turned off during the presentation. Feel free to actively participate in the webinar by writing your questions in the chat or saving them for asking during the Q&A session after the presentation. So today we see more on the PillarHall use in the academic research, but I will also like to remind you that these PillarHall chips are widely used in the industry, especially by the tool developers in the semiconductor industry. Here is one such example, that is the use of PillarHall chips in the development of a pure ozone generator. This is from Maiden Shah. This has been presented during this ALD 2023 conference. This pure ozone generator from Maiden Shah produces extremely high concentration, high purity, and long lifetime ozone gas when compared to the conventional ozone generators. The study shows that the pure ozone could improve the film formation in the ALD process. According to their experiments, the penetration depth using this pure ozone generator, they were able to improve the penetration depth of the thin film by more than 10-fold as compared to the oxygen plasma. So if you want to see the more information, please visit our website for looking into this blog post about this pure ozone generator. I will also like to say a few words on our ongoing conformality research competition. In order to increase the conformality research, we launched this conformality research competition, or like academic campaign. This is we are targeting this ALD 2024 conference presentation, and this is only for academics. And with this academic campaign, we are giving a 50% discount on our PillarHall chips, and there is a limit. There is you can take this 50% discount for maximum 10 PillarHall chips, and this campaign will be only till January 2024, or like we have only limited stock of the PillarHall chips for this academic campaign. Once this PillarHall chips finish for this academic campaign, then it will be the end of the academic campaign PillarHall chips deliveries. So please make sure that you will you get these PillarHall chips before the ending of this academic campaign. And here we consider both experiment and modeling results, and also not only the PillarHall chips, but also the conformality research based on any other high aspect ratio structures are also considered for this conformality research competition. And the winner will be judged by a team of experts, and the winner will be announced during the ALD 2024 conference that is held in Helsinki. Now, let's turn our attention to Professor Erwin Kessels, a distinguished figure in the ALD community. For those who are already familiar with Professor Kessels, you know we are in here for a treat. For those who are new to the ALD community, let me provide a short introduction to our esteemed speaker today. Professor Erwin Kessels is a professor at the Department of Applied Physics at Eindhoven University of Technology. In addition to this professorship, he also serves as the scientific director at a Nano Lab at Eindhoven University of Technology. Once again, thank you, Professor Erwin Kessels, for gracing us with your presence. So the stage is now yours, please.
Thank you very much, Anish. It's a pleasure to be here, and I welcome everybody that is attending this webinar. Let me show the. Let me start the presentation. Wait a minute. Okay, well, thanks once again for attending. It's really a pleasure to be here and to talk to you about conformality, and more particular about the conformality for plasma enhanced ALD. Let me also close some things here. All right. So, well, first of all, I have been introduced. I don't want to say too much about it more, but I am a full professor at the Eindhoven University of Technology, where I have a long history. I started there also as a PhD student. But in the early days, when I started as an assistant professor, I also started up the ALD activities. So I have been working on ALD already for more than 20 years. And in addition to ALD, we also work on area selective deposition and atomic layer etching. And one of our main expertise is certainly also plasma physics. So that also explains the topic of today. Furthermore, I also started the Atomic Limits blog. You might be familiar with this, but if not, I would like you to check it out, and I will refer to it several places throughout my presentation. And I'm also the founder of the ALD Academy. Okay, so the outline of this webinar. So I will start off with an introduction, and the first message will be that the future of semiconductor chips is really 3D. So that's the first point I want to make. And ALD is really a solution for that. And ALD can be used to deposit conformal films. And I will address today how well plasma enhanced ALD can do this too. So that will be a central question. And I will show you quite a few things of our research, recent research, where we have done conformality experiments with the chip matrix PillarHall chips. And I will start off with some thermal ALD to illustrate the so-called growth regimes for ALD. And then I will turn to plasma enhanced ALD, temporal ALD at low pressure, but also spatial ALD at atmospheric pressure. Time permitting, I also will show that you can use PillarHall chips also for other things than for conformality. And if I have time, I will show that you can also investigate the role of ions during plasma enhanced ALD. And then I will conclude and summarize. Well, the first thing, as I said, that I would like to point out is that the future of semiconductor chips is 3D. And I think most of you are very aware of this. So more than 10 years ago, all the field effect transistors in our electronic devices were planar field effect transistors. But since slightly more than 10 years, we went to the FinFET technology, which is, for example, in your smartphone. I'm quite sure that you have FinFETs. And the next step will be that we go to gate-all-around FETs, where you have the gate all around the channel material. And then even some more complicated structures are foreseen. For example, at the upcoming conference, the IDM conference, Intel and TSMC will also show that you go to gate-all-around FETs, but also stacked P-type and N-type on top of each other. And that's what we call complementary FETs. So you see, it's getting more and more in the third dimension. Now, a similar thing holds for memory. In memory, we went from 2D NAND. You might remember the memory sticks that we used to have. We went from 2D NAND to 3D NAND. And 2D NAND, all the memory cells were next to each other on a planar surface. But in 3D NAND, we also start stacking them on top of each other. So we're starting using, basically building skyscrapers. And here you see a 72-layer 3D NAND structure that is something like that is probably in your smartphone. And this is really the state of the art, something that has been reported by now. It's not available commercially yet. It's 321 layers stacked on top of each other. So 321 memory cells. And you can see you get to very high aspect ratios. Here, the aspect ratio is already 50, and this is then, even much more than that. So this is for memory, for NAND, but also for DRAM, we see something coming too. In DRAM, we have already quite used the third dimension because we are depositing already films on pillars, as you can see here. And this is already also in our devices. But the next step is that we make this even much more advanced, and we go the same way as the 3D NAND, as in the 3D NAND, where we now start stacking the memory cells by flipping them over and then stacking them on top of each other. So also here we go into the third dimension even much more. Now, so these are the trends that are going on, and I guess you are aware of this. And to enable this, we really need several things, such as conformal films. Yeah, so here you see the FinFETs again, and you see the films that are deposited very nicely conformally over the structure. And that's what we need. And here you also see fork sheet FETs. This is in between FinFETs and complementary FETs. You see very nice conformal films. And it's not only that we have the vertical structures, we also see these lateral structures. Also, and this is related to this, we also need gap fill. Gap fill is already there, of course, in our current technology, and this will get more advanced in the future technology, but also we will have lateral gap fill. Yeah, so we have conformal films, but we also have to fill up some of these spaces. Well, this is something that is a clear processing challenge, and it's not easy to address this, but as I will show, ALD can do the job. In addition to that, just for clarity, I think there are many other challenges. We also will implement new materials. We start with a method such as area selective deposition to topographically selective deposition, all to enable this trend towards 3D. Now, just a sidestep for those people that are not that familiar with this. So I might have already used the word aspect ratio. The aspect ratio is basically the dimensionless parameter that characterizes that is basically the length of this structure, the depth of this trench over the width of the trench. So a high aspect ratio means that you have very tall structures. And then conformality means basically how well the film is following this the structure. If you have a conformal film, the thickness is the same everywhere. So obviously this is not a very conformal film. So that's what we mean with conformality. And the principle, we distinguish conformality in terms of thickness. So this shows the thickness. But in principle, we also have to look at the conformality of the material properties. If the material properties change a lot over the structure, that is also something that can be pretty problematic. Okay, so as I said, we have these trends, and going to more 3D is a very, very clear trend that we have just seen. And this poses quite some challenges for the fabrication of devices. And the basic fabrication processes are deposition, lithography, and etching. And for deposition, there's one method that can really address this trend towards more 3D, and actually address this trend to higher aspect ratios. And that is plasma enhanced, sorry, that is ALD, and including also plasma enhanced ALD. Now, still, it's not a trivial thing. Still, there is a lot of research and a lot of efforts need to be done to really enable this. But I think these methods should be a good starting point. And that's basically what we will be talking about today. So, well, I think most of you also are familiar with ALD, so we will not go into detail here, but I think you all know that ALD is a CVD-like technique in which you deposit materials atomic layer by atomic layer, and you do this by repeating cycles. And every cycle typically consists of 2 half cycles, half cycle A, in which we dose the precursor, and half cycle B, in which we dose the co-reactant. What is now very important is that you have self-limiting surface reactions. So the film growth should really stop once you have reached a certain exposure for the precursor and also a certain exposure for the co-reactants. So this is extremely important. And that feature also explains the fact that ALD is very well suited to deposit conformal and uniform films. And this is different from methods such as PVD or PCVD or CVD, because these methods, they are basically flux controlled. If you look here at the side of a wafer, for example, the flux will be less, and therefore also the thickness will be less. And especially here, if you have this complicated 3D structure, the flux at this corner here will be much lower than here. And that means that you have less film, or maybe even no film over here. So these methods are flux controlled, and this is different from ALD because ALD is surface controlled. If you are working in saturation and you wait long enough for all the exposures, the thickness is the same everywhere. Of course, how fast the saturation is, that depends on the flux. So you might need to wait a little bit longer to really get to saturation here. But in the end, if you wait long enough, then the thickness is not flux dependent. That's why we call this a surface controlled method. Okay, so I talked about ALD, and a little bit about the plasma enhanced ALD. It's not very different. The main difference is that the co-reactant step is now a plasma step. For example, here we typically use water or ammonia, depending on the material that we're depositing. And if we replace this with a plasma step, then we get plasma enhanced ALD. And I have a little animation that is nice to show, I hope. This is a plasma enhanced ALD process of aluminum oxide, where we use trimetal aluminum as the precursor and oxygen plasma as the co-reactant. And we're zooming in here at the surface. The surface is hydroxyl covered, and we expose this to trimetal aluminum. The trimetal aluminum reacts with the OH, actually making aluminum oxygen bonds and splitting off volatile CH4. And now this process is self-limiting. It will stop when virtually all the OH is consumed. We purge and then introduce oxygen, and we strike the plasma. And the oxygen now will combust the CH3 groups, in this particular case, making water and CO2, and replacing the CH3 by OH groups. Again, this is a self-limiting surface reaction. And then we have an OH-covered surface. And we can start all over again for the next cycle. And this is how we build up our film. As you probably are aware of, this is not very different from thermal ALD, apart from the use of the plasma. Now, it's good to know that plasma-enhanced ALD is very widely used commercially. There are many applications in commercial products where plasma-enhanced is used. And that holds for oxides and nitrides and probably even for metals. And the reason that people use plasmas are that there are certain merits. You can have improved material properties. And certainly if you want to work at lower temperatures, this is really enabled by ALD. Also, some materials are very difficult to do with thermal ALD, and then plasma-enhanced ALD often provides a solution. And there are precursors that are sometimes not very reactive thermally. So then the plasma excitation or the use of a plasma also is helpful. And there are some other merits too. Of course, nothing is for free in life. There are some challenges too. So of course you need a plasma source. So you add, that adds to the complexity of the system. You can have plasma-induced damage, so you have to always be careful with this. And another one that is always a question mark is about the conformality. Is the conformality as good as for thermal ALD? Well, that will be the topic of today. It's probably not always as good, but it can be very good. That's already a little bit the spoiler for today. And as a matter of fact, in Eindhoven, we have been, and we are still investigating all some fundamental aspects of plasmas. So if you have a plasma, you have different species, you have photons, radicals, ions, electrons. They have the surface reactions. They can be beneficial reactions. They can be detrimental reactions, such as damage. So we have to understand that. We also have to understand the transport of species, certainly reactive species, in trenches and 3D structures, obviously, now after this introduction. We have to understand what happens, what are the reaction products created, how do they maybe react in the plasma again, how we can read the position. These are the things that we have been addressing in Eindhoven, and we still are working on this. And today, as I said, I will look at the conformality. Before I really start with the results, I would like to say two other things. Actually, first of all, I would like to advertise the ALD database. If you're not familiar with this, I think I would suggest looking it up. If you go to atomiclimits.com, there is this button here, and then you can access this database, because this gives an overview of all ALD materials. I'm sorry, all the materials that have been deposited by ALD and reported in the literature, of course. We don't know what people have done without reporting. So you find this periodic table, and you can click an element, and then you find all the materials that have been prepared, including the precursor and the co-reactants, and also with direct links to the publication. It's crowdsourcing, so if you develop your own process, please add it to this database. We will have a look, and we will then make sure that it will also show up on the website. The other thing that I would like to point out is that most of the results have been done in have been obtained in a clean room, where we have several ALD reactors. I think it's always good to see what kind of reactors we have used. So in a clean room, we especially work with oxide-Linzmann systems. And we have these systems where you can do plasma ALD and also thermal ALD in one system. And today, I will show mostly results that have been obtained with inductively coupled plasmas. So that's what we have used for most of the results today. We also have another lab where we have home-built systems. And I will also show today some results that we have obtained with a spatial ALD reactor. And this works at atmospheric pressure. So that will be coming later in this webinar. Okay, so that was the introduction. Now I would like to report about conformality experiments. And before doing that, I would like to highlight that there are many good quality papers out. So I will not refer to them too much today, but I want to point out that there's some great work. For example, the early work by Roy Gordon. There were some nice papers also by the Ghent group and by the ALTO group, Rika Perina. There were some very nice papers about conformality in ALD. There is even a book that addresses this. And also on our website, you find a blog with some nice animations. So there was a lot of resources are out there, and was much more than even this. The first thing that I would like to address is that we can distinguish several growth regimes. And it's good to have some understanding of these growth regimes when you think about conformality. And for thermal ALD, we typically distinguish two growth regimes. One is reaction-limited growth, where the reaction is slow, and you can easily get conformal films. And the other one is diffusion-limited growth, where your species, you're transport limited, and then you have to wait long enough for the transport to go into the trench. This depends a lot on the sticking probability, which one growth regime you are. Later, I will come back to energy-enhanced ALD, particularly plasma-enhanced ALD, where another growth regime can happen, and that's recombination-limited growth. And then the recombination probability is really important. But for now, thermal ALD, reaction-limited and diffusion-limited. And of course, studying conformality, you need certain structures. And of course, you can use trench structures or pores or vias, whatever. And I show here some samples that are made with different aspect ratios. And you can deposit films on top of this, and then you can do the analysis. And this is a nanolaminate, which makes this a pretty image, I think. And then you can study the conformality, of course. But you need to make a cross-section, and you need to do TEM measurements, for example, for this. And it gives great results and great images. But of course, to really study things a little bit more quantitatively is quite difficult. And also it takes a lot of time and money actually to make these structures. So it's very valuable to do this. but it's also very nice to have like another opportunity. And as you know, and you are here on the webinar of chip metrics, I think that the PillarHall structures from chip metrics can be very, very helpful for this. And these are basically lateral trenches. They're called also lateral high aspect ratio structures. So these are little chips with having these structures on top. And basically the structures are a membrane suspended over the substrate. And this little membrane is supported by very tiny pillars. And that makes it the PillarHall chips. And in this membrane, there is a slit at some point, and that makes this now a cavity. And what you can do is deposit the film on top of the structure. And then, of course, if you have a conformal film, the film also will go into this cavity in this lateral high aspect ratio structure. And the more conformal your film is, the deeper there will be the penetration. So the penetration depth will say something about the conformality of your process. Now, the nice thing of these PillarHall chips is that you can remove the membrane quite easily with Scotch tape, and then you can look at this film thickness nicely with optical imaging. Reflectometry, you can do spectroscopy refractometry, and you can really measure the thickness profile. And from that, you can determine the thickness conformality. Moreover, in principle, you can also look at the material properties. And that's also something that we have done. You can check how the material properties depend on the position. So I think these PillarHall experiments can be very nice to really study this conformality a little bit more in a more advanced way, and also in a quicker way. So that's what we have been using. Now, some theoretical stuff that I need to define. So first of all, we're going to look now at the sticking probability. And the sticking probability of a precursor or a co-reactant species is the sticking probability S0 is the sticking probability at an unoccupied or unreacted site. If the site has been reacted, then the sticking probability occupied, if the site is occupied, the sticking probability drops to 0. So an open site, it's S0, and when the site is occupied, the S0 is 0. And this is helpful if we start modeling the exposure. And I will not go in extreme depth, but I would like to show you that typically we start with a surface that has not reacted, and we expose it to the precursor, and the precursor starts reacting. It reacts with the open sites and starts to occupy these sites. And then you go from 0 coverage to coverage close to 1. 1 is full coverage. And you have this trend towards this. And this is basically the saturation curve that you will have. So you start with coverage 0, you go to coverage 1. And the sticking here is S0 for if it was coverage is 0. But the total sticking probability or the link stop sticking probability will decrease, of course, because the coverage goes up. So the coverage, the sticking on an open side stays the same. But for the whole surface, the sticking will reduce. So the lumped sticking probability will decrease with the coverage. And basically what you can do by doing this kind of analysis, you can write down equations. For example, for the coverage, it depends on the flux, and it depends on this lumped sticking probability. And basically this is a differential equation. And you can solve this kind of things. And that's how you can do some modeling. Well, this is things that we have done. And I will not go into all the details, but now we can look at these limiting cases. And the first one is the reaction limited case, where we have now introduced precursors here inside the trench opening, and the precursor will now go inside the trench. And we look at the coverage. And so this is the density of the precursor, and we will also look at the coverage. And when we have reaction limited growth, then basically the reaction rate, the rate for reactions is way smaller than the diffusion rate. And more precisely, this is the important factor that counts. If the sticking probability is very small, and sticking probability multiplied with the aspect ratio square, if that holds, this condition holds, then you are in a reaction limited growth. Because what happens is that your species will go inside the trench, the reaction is very slow, and they will kind of get a constant density, and then the film growth will start, because the film growth is the limiting factor. And you can write down all kinds of equations. I will not go over that in detail. But one of the consequences of this, if you're working in these conditions, is that your saturation dose, the dose that you need for saturation, is not different for this 3D structure than for just a planar surface. You don't have to extend it, because you get a constant density here, and the reaction is limited. So the saturation dose is the same as on a planar surface. So that's good to know. Now, this is different if you go to diffusion limited case. Now, the reaction rate is fast, and the diffusion and the transport is limited. And you can have this when the sticking probability is, for example, very high, and when you have value aspect ratios, then the transport is limiting. So the species are now going inside the trench, and they immediately react because the reaction rate is fast. And now you really see a diffusion profile, and you see actually a diffusion front going inside this trench. This holds for high sticking probabilities, but also for very high aspect ratios, of course. And now things are different, okay? You can write all kinds of equations, and now the saturation dose really needs to be extended, because the saturation dose now scales with this aspect ratio. You have to wait longer and longer compared to a planar surface, because you are waiting for the transport, and it goes with the aspect ratio square. So this is important to know, because if you are in this diffusion limited growth, you really have to extend your exposure time once you go from a planar surface to a 3D surface. Now, and of course, for the diffusion limited case, so it also depends whether you have a trench or a pore. If you have a pore, then the transport is even more limited. And then you even have to have a 4 times larger dose to really get into this saturation. So this is also important to know. Now, this is important for dosing and actually checking conformality, but with some additional aspects that is very interesting, because now, depending on the sticking probability, also this deposition front will look differently. So here, this animation shows this deposition front. And what we now see is that if you have a lower sticking probability, it's more smeared out. Well, for a high sticking probability, this diffusion front is much more sharp. And this now provides a very nice opportunity. If you measure this, the slope here, that provides a very nice opportunity also to determine the sticking probability. And the sticking probability, I said, is important to know this, because then you know whether you're really in the diffusion or reaction limited regime when you go to 3D substrates. So I will show you here some data that we have used to determine the sticking probability of water during thermal ALD of aluminum oxide. And we did this as a function of temperature. You can see here the slope of this deposition front, and from that we were able to determine the sticking probability and compare them with other work. And interesting here is that the sticking probability of water is pretty small. The water is not extremely reactive with the CH3 groups. It depends a little bit on temperature, but overall we see that the sticking probability is not very high. Now, this was a case where we are limited by water. In principle, we can distinguish then water limited case and TMA limited case. So if we decrease the TMA dose, at some point we get in the TMA limited case. And by working in 2 limited cases, we can actually determine the sticking probability of not only water, but also of TMA. And this is the way how you really can learn something about, well, the sticking probability of the process. And these data is very important for, as I said, finding out in which regime you are, but also in modeling. I mean, you want to know these kind of numbers. Okay, so that was thermal ALD and the growth regimes. Next, I would like to talk now about plasma enhanced ALD. And when you have a plasma, there is another factor that you have to take into account. You can have recombination of your reactants. Then you get into recombination limited growth. And I will illustrate this and I will explain this. I also want to point out that with ozone, if you are using ozone, you could have something similar. Ozone is also a reactive species that can recombine at surfaces. And then you also have to pay attention for this effect in principle. So that's also, I think, important to know. Now, it gets a little bit more complicated. I talked about the sticking probability. Now, the R is the surface recombination probability. And surface recombination can happen independent whether the site is occupied or unoccupied. Surface recombination is two oxygen atoms, for example, recombine to oxygen molecule. And this can happen at an open and at a occupied site. So R is independent of the coverage. Okay, so that's the sticking probability and the lump sticking probability. This is the surface recombination probability. And as I said, and as you might have figured out, the surface recombination of plasma species is important. Yeah, so the probability is R. Yeah, so oxygen atom can recombine with another oxygen atom from oxygen molecule. And once this happens, this oxygen atom is not available anymore for your surface reaction, for your ALD surface reaction. And what is important now is that if you have a trench and you have oxygen atoms diffusing down and hitting the wall several times, every time when they hit the wall, they can recombine. And basically, they can be lost for the process. And depending on the number of collisions, your flux will now decrease quite drastically. So when you have many wall collisions, it can be hard to get species down here at the bottom of the trench when this R value is significantly high. So that's why we need to know this R value. And here I have some R values that you can find in the literature. This is all non-ALD related literature. So people have reported about this hydrogen recombination or oxygen recombination from different materials. And you see it's radical dependent, but it's also material dependent. And now this is non-ALD surface conditions. So it would also be interesting to really determine this under ALD conditions. And that's what we also have done. Again, we can nicely use this PillarHall structures for that. We can do the same thing as before and look at how deep we get inside the trench. I'll show you some results. This is plasma enhanced ALD of silicon oxide, and where we varied the plasma time. And we see, this is top few images, we see that when we extend the plasma time, that we get deeper and deeper inside the structure. That shows that we are limited by the plasma here. Yeah? So otherwise, we would not see this. Also, I would like to point out that this is an aspect ratio of more than 800. So that's certainly not bad at all. This is actually a very nice conformal film. And here I show various materials. I will come back to this later. But you can also look at different materials, and you see it varies now on the material how deep you get. But I will come back to this in a second. Again, we did some simulations or some modeling, and so what is important to realize now is that the radical density depends now on this recombination probability. The radicals go less deep in the film if the recombination is higher. So this can be limiting your transport inside the trench. And basically, this is it actually decreases exponentially by this equation with the aspect ratio here and here the recombination probability. And that means also that the film growth will not go beyond the radical density. And there is some equations that you can derive. But what you can see here, that if you go to high aspect ratios, it gets exponentially more difficult. So this is the penetration, and the penetration is now becoming exponentially more difficult, as you can see here. And if you look at the time to reach saturation, then you have to increase the time exponentially long if you're going to a higher aspect ratio. So that is something that is very good to know. As shown, we can get 3D conformal films. This is silicon dioxide, and we still get, for a long plasma exposure time, we can reach down to an aspect ratio of more than 800. Yeah, so it's not bad, but it is something to be aware of. And as a matter of fact, by plotting this penetration depth over the cavity height, then we can plot this data, and we can use the equation that I just showed. And from the slope, you can extract the recombination probability. And we see that the oxygen recombination probability is not very high. It's relatively low for oxygen on silicon oxide. And this is also in line with what other measurements have shown. But now we really established it for real ALD conditions. We can do this also for different materials. So here are silicon oxide again. Titanium oxide, also here we can reach an aspect ratio of over 700 when we go to long plasma exposure times. For alumina and hafnia, it's way less deep, so it's very much dependent on the material. Still, this is an aspect ratio that is quite high for many applications. So many applications don't need aspect ratios more than 100, and for that, you still would be fine under these conditions. And from the analysis, we can determine the surface recombination probability, and we see it's heavily material dependent. So for silica and for titania, it's relatively low, but here you see it's higher. And that explains then why it gets less deep. And of course, we can have dependence on the processing conditions. We see some temperature dependence, not too temperature dependent, but we see some temperature dependence, we see some pressure dependence. So we can establish these numbers by these PillarHall experiments. It's good to have these recombination probabilities, and we can quite easily get this out from the analysis of the PillarHall structures without having to go to TEM, where it would be very difficult, I think, to extract these numbers. And this adds now to our understanding. We better understand now how radicals diffuse down a high aspect ratio structure and the wall collisions where you can have recombination, etc. This is what we have now, a better understanding of how that happens. And this is what we can use to optimize our ALD, the plasma-enhanced ALD processes. Now, this was a typical low pressure system that we have been using. Recently, we also have started working on spatial ALD, where we actually work at atmospheric pressure. Spatial ALD is a very interesting method, and we also were interested in, how conformal can you go with spatial ALD. Now, spatial ALD is slightly different from temporal ALD. So this is the regular ALD case where you have a static wafer, and you dose the precursor and the purge and the gases one by one as a function of time. Here, you inject them statically, and now you move your wafer with respect to the injection zones. In both cases, you will build up the film thickness atomic layer by atomic layer, but how do you do it is slightly different. Now, for spatial ALD, often we use atmospheric pressure because then you can use the purge gas to really separate the precursor from the co-reactant. So not always, but in many cases, spatial ALD works at atmospheric pressure. And that, if you think about our lateral trenches, has a consequence. At low pressure, of course, we have, for temporal ALD, we have mostly wall collisions. So we are working in the Knudsen regime. But now, if you get to atmospheric pressure, you can have gas phase collisions for the radicals. The mean free path is smaller now than the dimension. And that is something you have to take into account. So that's one challenge. And of course, the plasma, that's the other challenge. And we'd like to understand how this develops. Now, what I will show is some work that has been done by a PhD student, current PhD student, Mike van der Pol. And this work that I will show will appear very soon in Applied Physics Letters. It could be today, it could be tomorrow or next week, but it has just been accepted and it's ready to be published. So if you want to read more about it, just check the Applied Physics Letters website. Okay, so plasma-enhanced spatial ALD, we use this rotary reactor where we have wafers or substrates that we rotate underneath the precursor injection and also the plasma exposure. And so here is an animation, and this is what we used. The precursors are shown here for silicon oxide titania. They're the same as for the low pressure case, and the plasma is atmospheric pressure, and it's nitrogen diluted oxygen plasma. And what we can do, we can change the rotation frequency, and when we change the rotation frequency, we can vary the plasma exposure time. Note that these plasma exposure times are very short, way shorter than we showed before, and this is actually one of the benefits of spatial ALD. Okay, let me show you some results. This is some microscopy images for silicon oxide titania. It's not so easy to see on this screen, but we looked at the penetration depth and we could really establish that the material penetrates deeper in the structures when we increase the exposure time. And what we found out is that aspect ratios larger than 50 here and larger than 200 here can be covered conformally by plasma-enhanced spatial ALD, even at these short exposure times. And that is maybe even clearer here when I show the thickness profile. This is thickness profiles measured by spectroscopic lobsometry. We can see that the thickness, that the material goes inside the trench to a pretty high aspect ratio. For 74 here for silicon oxide for this plasma exposure time, and for titania, it even goes deeper for less than a second of plasma exposure time. So these are very nice results, and this shows that you can deposit these materials nicely conformally in high aspect ratio structures by plasma-enhanced spatial ALD. Obviously, we also like to see whether we can do some modeling and extract some parameters. We can use the same model as I showed before, but then we had Knudsen diffusion. So things become a little bit more complicated now. We have to take the diffusion, the collisions into account. So we have the molecular diffusion case, and you can do some analysis. And Mike Grollo did this. We can see the different cases. It turns out that for the condition that we use, we are in a kind of a transition regime between Knudsen diffusion and molecular diffusion. So we are on this transitional regime, and then you can do the math, and then you can find a different parameter here, and that's what you can then use to determine the recombination probability. And that's what we have done. Here we have plotted again the penetration depth of the cavity height as a function of the exposure time, and we see that we have nice data points that line up pretty nicely on this equation, and from that we can calculate now the recombination, the surface recombination probabilities. And this is all done at atmospheric pressure, so these are the numbers that we find. And these are also low numbers, as we saw before. And as a matter of fact, pretty surprising, I would say, they are not too different from the low pressure case. So there's a huge difference in pressure. And these numbers are not too different, I would say. So the pressure has a fairly limited effect on the surface recombination probability. That's what we learn here. And this is important that we know about this, because often we would like to know the saturation time, at the time, the plasma exposure time required to reach the bottom of a trench. And by using these results, the data on R and also our data points, we can now calculate how long it takes to cover a certain aspect ratio. We see that it takes longer. Of course, you have to go to high aspect ratios. We see that it takes longer for silicon oxide than for titania due to the larger R. We also can compare it with the low pressure case. And then we even see that there is a region where it's faster. It can be, you can be faster at low aspect ratios than with spatial ALD. than with temporal ALD. So that actually is all pretty interesting and surprising results. Okay, given the time, maybe a few words about this. We can also do other things with PillarHall chips. I will not go in very great detail. I do want to point out that if you do plasma-enhanced ALD, you have ions, and ions are accelerated in the plasma sheet that forms very close to the substrate. There's a potential drop, and this accelerates ions. They become energetic, they get ion energy, and they become directional. And if you do now measurements of the ion energy, what we found out is that the ion energy is typically under grounded conditions. It's maybe 30 electron volts, 20 electron volts. So the ion energy is relatively low, and the ion flux is also not that high. So we expect maybe some surface reactions to be activated, but we don't expect damage or these kind of things. But still, we were wondering what exactly could happen by these low energy ions. So now we did experiments where we had a grounded substrate and we measured the ion energy. And we can see here we have ion energies less than 30 eV. So these are not high energies, pretty low energies. And we started to deposit films inside the trenches in this PillarHall experiments. And then we realized that inside this cavity here, you only have oxygen atoms. Ions will not make it. Ions are directional. But here at the opening, you have oxygen atoms, but also ions. So now we can distinguish between this region with ions, with that region without ions. And that's what we did, and we found some very interesting results. So here's silicon oxide again. This is within the trench, a certain growth per cycle or certain thickness, independent on the plasma exposure time. But inside the trench, we see a lower thickness, a lower growth per cycle, but we even see that the plasma exposure time matters. And now looking at the quality, given here as the red edge rate, the lower the red edge rate here means that this is better quality material. And also we see that the material improves when we have a longer plasma exposure time. So this is also something that we could establish by these PillarHall experiments. And as a matter of fact, we saw that the growth per cycle really decreases with the ion exposure due to the ions, and that the material quality improves with ion exposure, again, due to the ions. So this is something that we also could get out of this data. And as a matter of fact, we were able to have a lot of data, and we were able to plot them all on one curve if we used the ion energy dose as the main parameter, which is a product of the plasma exposure time times the ion flux times the mean ion energy. So this was really some nice results that we could also get out of the PillarHall experiments. And we could not only get this out of silicon oxide, we saw something similar for titanium oxide. Titanium oxide, we also saw a difference between the ion exposed region and the region in the trench. And I will not go in detail now, but here we found basically that it is the crystallinity that's different. Here the material is crystalline, where you have ions, and here it's amorphous. So the message here is that these PillarHall experiments allow even for other things than just checking the conformality. And well, we at Eindhoven were pretty excited by this kind of results. Okay, that was a lot of information. I've come now to the conclusions. I think it's clear that ALD has an excellent conformality, and it really enables the trend towards the complex 3D structures. I would not know how we would solve that otherwise without ALD. Note that plasma-enhanced ALD is widely used commercially. Thermal ALD is not always an option, but there have been, and there still are, of course, questions regarding its conformality, and we have been addressing them, and we keep on addressing them. We do this partly also with the PillarHall chips, because they are very powerful to investigate the conformality. You can be faster, you can be cheaper, but also, and I think this is maybe even more important, they provide additional opportunities and insight in the process. Now, I've shown that plasma-enhanced ALD can yield conformal films, highly conformal films, but it does depend on the material and the plasma conditions. And I showed this for temporal ALD at low pressures, but also now with some recent results for spatial ALD at atmospheric pressures. You can still use them. And then I think the most important bottom line of my work, of the work presented, is that of course we need a good understanding. This is important scientifically, but also for technologically. It's important that we understand what we're doing. We have to understand the growth regimes. We have to understand things like sticking probabilities and surface reaction probabilities if we really want to get everything out of the method. And that's the most important message of today, I think. I do also would like still want to say that you can use these PillarHall chips also for other studies, and I showed this ion surface interaction. That brings me to the acknowledgements. I would like to acknowledge the group, also the companies that have been that we have been partnering with in this research. Special thanks to these people, especially to Karsten Arst and Mike van der Pol, which are the PhD students that are working on these PillarHall chips, but of course also the other people mentioned here. And I would like to thank you very much for being here and for attending, and maybe for asking questions. So that would be the next thing. If there are any questions, we will start addressing them right now. But thank you very much.